Good morning, good afternoon, good evening, depending on wherever you're listening this from or watching this from. Welcome to Weekly Science Review, organized by Vetri Labs. Here we take open science articles that are published in the field of electrochemistry and then do a critical review with someone leading the discussion. We at Vetri Labs focus on enabling implementation of electrochemical technologies at scale. Today's discussion is going to be led by Mani Ramani. Mani Ramani is the Director of Engineering at Plug Power. Over to you, Mani.
Yeah, thank you. Let me share my screen here. Okay, can you guys see my screen?
Yes.
Okay. Yeah, so today we're going to talk about the enhancement in the selectivity and sensitivity of nickel and palladium functionalized molysulfide toxic gas sensors. This is authored by Levna Chako and a few other people. It was the Electrochemical Society publication. So we'll just start with the...
Mani,
yeah.
If you go into presentation mode, it may help a little bit.
Yes, sorry, yeah. Okay, is that okay now?
Yes.
Yeah, so gas sensor, typically existing materials that are used are organic materials, polymers and porphyrins, some complex associated with the porphyrins. Metal oxides, there are some drawbacks with the metal oxides. They have to be heated, and they're not really that selective in terms of some of the graphene structures have been very popular of late. There's also carbon nanotubes and molysulfide. This publication focuses on functionalizing molysulfide, and the rationale behind that is by functionalizing it, they can get high selectivity to specific gases. It also gives them, in some cases, multi-component capability. It also limits some cross sensitivity, and obviously, in terms of gas sensor, you want to have low drift, which is relative response over the time of testing. And so they have tried to compare the molysulfide against the functionalized molysulfide, which includes, I think we've taken palladium, nickel, and zinc oxide and functionalized on the molysulfide. So that's the publication we're going to be talking about today. General applications of the gas sensor. Nitric oxide detection is an environmental pollutant coming from automotive sources, furnaces, and power plants. These are typically the sources, and wherever there is nitric oxide, you can have a gas sensor and you can detect it and feedback and operate the furnace and power plants differently. Biomarkers for diseases. This was very interesting. For example, if somebody has a chronic pancreatitis, hydrogen sulfide and NO are actually in their breath. So you can use this sensor to detect the diseases as well. And in general, volatile organic compounds, some of these sensors can be applied to detect volatile organic compounds. And also in HVAC, if it's a refrigerant, ammonia is a refrigerant, and ammonia leak can be detected when you use sensors in applications with ammonia. And humidity, in HVAC, you can use these sensors for humidity detection as well. So that's just a general overview of the gas sensor. Sorry. Give me 1 second, Chuck. I just have to stop sharing to move my screen.
No problem at all. No problem at all.
Can you see my screen now?
Yes, but please change it to presentation.
Yeah, and unfortunately it gets stuck in the presentation mode.
Oh, okay.
Maybe just
No problem. We can go.
No, that's fine. Oh, it moves now. That's good. Okay, so why moly sulfide as a gas sensor? As a gas sensor, the gas has to absorb on the surface. So there's a binding energy for the gas against the specific material that needs to be appropriate. So, and the material should have a high surface area to volume ratio. And the material should also be able to be doped so that we can enhance the functionality or selectivity to different gases. Typically, moly sulfide is a good catalyst in desulfurization in petrochemistry. It's also used for hydrogen evolution. So as a catalyst, it's a pretty decent material. In addition, it also has semiconductor properties. So you can adjust the band gap and tune it so you can make it a photodetector or a microelectromechanical device. So it's flexible and it has optical properties. In addition, for the purpose of this paper, the volatile biomarkers, which we talked about, the H2S sensing and the nitric oxide sensing, and then the toxic gas detection, which is they were focusing mostly on the environmental, the automotive emissions, like ammonia, NO2, and sulfur dioxide, for example. This paper, they focused on NO and NO2 predominantly. So the focus on this paper again was they doped the moly sulfide and compare the moly sulfide, base moly sulfide with functionalized with zinc oxide, nickel, and palladium. Hydrothermal process was used to develop these materials. We'll just go over the fabrication in a second. And then after all the material was processed, there was a device that was, the gas sensor was fabricated, and it was tested using 2 electrodes, and they applied a voltage bias, and they monitored the current as a response to some of the gases that were in the challenge, some of the challenge gases. Going to the next slide. Device fabrication. In terms of material preparation, it was a solvent wet chemistry based process. And hydrothermal process is also called solvothermal. If it doesn't include water, it's called solvothermal. This included water. So starting point precursors were sodium molybdate dihydride and thiourea. In 12 hours at 200 C in autoclave, they make these moly sulfide flakes or particles, and then they sonicate it to suspend them out of the solution. And these are nano flakes. And then you can additionally functionalize each of them, or each of the type of material you want. The zinc oxide, you can add zinc oxide nanoparticles. For nickel, you can add nickel precursor, that's a nickel acetate precursor. For if you want to add palladium, if you want to add functionalize with palladium, you add a palladium 2 precursor. And you get each of these material that are then put on the device with the N-type semiconductor. First, obviously, you clean the semiconductor, and you're putting the material. You're actually putting the material on silicon wafer. So you're growing silicon oxide with using a thermal oxidation process. And then you put pad contact, or using patterning, which is photoresist and the typical semiconductor process. You put chromium and gold pad contact, and then the MOS2 material with either functionalized or just as MOS2 is transferred to form that structure shown here. And in a Z direction or an XY direction, that material is kind of shown in that path where there's the current collector is shown, which ties that moly sulfide functionalized material onto that wafer. Sorry. Okay, material characterization. So they further took the material and did XRD and Raman. And if you look to the left, they showed the moly sulfide is the bottom of the XRD chart here. You can see a 002 peak, which shows the crystalline moly sulfide, hexagonal crystalline moly sulfide. And then as you grow palladium that's on top, you can have a typical signature 200. And then as you go to nickel, really there's really no clear signature with nickel. Zinc oxide is a very clear signature. Just to confirm, they do an EDS as well. And that confirmed that they did get structures with nickel, palladium, and zinc. And on the right side, if you look at the right side, those are the shapes that are gotten with each of the materials. So that's molysulfide, and each of these materials have curly structures. It kind of shows you the high surface area volume with these materials. So they've kind of shown that they have coated, functionalized each of the structures with nickel, palladium, and zinc on top of the molysulfide. Next slide. So the main fundamental aspect of this is the semiconductor aspect of molysulfide. And when oxygen or oxidizing gas comes in contact with molysulfide, it adsorbs on the molysulfide, it attracts an electron, and it depends on the temperature of the material and the oxygen molecule. It forms different adsorbed species, either as a molecular or an atomic oxygen. But there is a charge transfer that happens between the molysulfide and the oxidizing species. In this case, it's shown as oxygen. And the charge transfer pulls electrons from the conduction band, which depletes the electrons at the conduction band. And this, if you have a circuit, if you apply a voltage and you measure current, or you measure the resistance, you would see that as the conduction band is depleted, the resistance of the material actually goes up. So if there is more, in this case, let's say, then the resistance should go higher and the current should drop. If there's a reducing gas, the opposite will happen. The conduction band gets supplied with a lot of electrons, and that gives more current through the device, and the resistance goes lower because there's more electrons in the conduction band. Typically, this is the principle of operation. Just to continue on, for this device specifically, the oxygen is grabbed onto the molysulfide electrode, it is withdrawing the electrons, and essentially it forms a O2 minus ion there. And O2 minus charged species, obviously it generates a high resistance because the electron is removed from the conduction band. And if you supply a toxic gas in addition, it depends if it is either oxidizing species or reducing species. If it is oxidizing, again, it will increase that electron withdrawal above what you have with the oxygen in air, and that will change the resistance of the circuit. So if you have air and then you have toxic gas in air, that should give you a clear signal between the resistance, just bare air, pure air, and then the resistance with a toxic gas in air. And if the toxic gas is reducing, that should replenish electrons in the conduction band, which will then reduce the resistance and increase the current. So it depends on if it is an oxidizing environment or a reducing environment. So these are, they developed a VI curve pretty much with any device, electronic device. You develop a VI curve just to get a baseline signal. And this is with just air. This doesn't have any sensing gas on it. So this is just to baseline the device performance against pure air. So, and these are the resistance values. The nickel molysulfide is about 202 ohms, the molysulfide 210, with the zinc oxide slightly higher. Molysulfide itself, as a pure material, it's 170 ohms. Some of these are photoreceptive. This one, particularly the palladium doped molysulfide, is photoresistive. and photoresponsive, I should say, and the resistance does drop when you turn on the light. Again, remember, you can excite the conduction band. You can excite electrons from the valence band to the conduction band as well. So there is multiple approaches in changing the resistivity or the resistance. One is if you change the way the charge transfer occurs at that interface, just through a gas phase to solid phase charge transfer, or if there is a photo application or an external excitation that can also input electrons from valence band to conduction band. So that's part of this photoresponsive behavior. So what this means is the gas response has to be done in a specific environment, either dark or light, which will affect your background current. As long as you keep the same condition, they argue that the repeatability of when you add a specific gas would be pretty good. Sorry, I have got into the problem again. Stop sharing for a second.
You can continue in the non-presentation mode if you want to.
Yeah, I probably should do that. Okay. Okay. Do you see it?
Yes.
Yep. I'm going to try it one more time just to see if this works. Okay. So the test was, once the device was fabricated and the baseline curves were taken, they started the challenge gas test, which is, in this case, there's a lot of charts here I'll walk through. 2 ppm of ammonia, 2 ppm of hydrogen sulfide, 2 ppm of nitric and nitrous oxides were the challenge gases. And the goal is obviously to have at least one of them and to be able to dial in a particular level of sensitivity to these gases. So the A figure there, which is just molysulfide, doesn't really show clear separation in signal between these gases. And they obviously take the air, they take it from air, which is at 0% response, and then they put hydrogen sulfide where the response goes -30. And the way they define the response is the delta current over the initial current. And delta current is the current during gas exposure. And I naught is current during air exposure. We know I naught because we've already established, or they've already established the VI curves for each of these materials. So that's a given. The IG is just the current during specific gas exposure. For example, when you expose it to H2S, there could be a particular value, and then you separate, you subtract the air exposure, divide that, and that's your response that they're plotting here. So with hydrogen sulfide, it goes down to -30%, which kind of implies that the current actually goes down, meaning the resistance goes up. And with the same thing happens with the nitric oxide, the nitrous oxide, and the ammonia as well. With the zinc oxide, there is signal. So all of these gas species adsorb and charge transfer in a similar way, except if you look at the nitric oxide, there is a clear separation in signature compared to the nitrous ammonia and the hydrogen sulfide. And the same to say about nickel, there is a clear separation with hydrogen sulfide. So moly sulfide doped with nickel as a clear signature with hydrogen sulfide, so it's more selective to hydrogen sulfide. Moly sulfide with palladium is the one material they show that the response actually goes the opposite way. And if you look at it, the same nitrous oxide in the zinc oxide scenario shows a negative response. And the same nitrous oxide with palladium, moly sulfide doped with palladium, shows a positive response. It's the same gas, but two different responses. And their theory is it is due to the chemical potential of nitric oxide with respect to the chemical potential of molysulfate palladium or with respect to the zinc oxide. Obviously, the chemical potential gradient will drive electrons one way or the other. And in addition, most of these functionalization looks to alter the way the bonding energy work. So it depends on, it affects how these gases bond to the functionalized materials. And some of these functionalized materials, for example, palladium with molysulfide, it has a different or higher work function, which also now has the ability to give electrons easier than molysulfide. So it does impact the way the sensor operates. And then in addition, there is a Fermi level alteration that happens, especially when you put nickel and zinc oxide, which is essentially how far in you can dig in for the electrons from the conduction band. So there's a lot of mechanisms that they rationalize for the in benefit of functionalization, but the functionalization is definitely unique in terms of which gas you have to be selective to. And then once they add signal with moly sulfide nickel doped and moly sulfide palladium doped, they continue to change the gas concentration. So they use the same gas now that they know the moly sulfide nickel actually was very selective to hydrogen sulfide. So they on the left side, graph A and C are comparable. And there's moly sulfide with H2S, and different concentration was picked on A, 0.3 ppm, 0.5, and 0.8, and 2 ppm. And they look at the response and they plot the kind of a calibration curve, gas response versus gas concentration. On the plot B, what's shown is moly sulfide with palladium doped, and they try nitric oxide, and that's again the only one they're published that shows a positive response. And they have again developed the same kind of sensor calibration curve. And the bottom C and D are just repeatability curves. The bottom C, the C curve is on 2 ppm hydrogen sulfide. It does repeat pretty well when you go back to 2 ppm hydrogen sulfide and then come back to air. It goes back almost to 0. And then on the D, response D, there is a drift, as you can see, but it is relatively responding to half a ppm of nitric oxide. So anyway, this two materials, combination of these two materials would be a great biomarker for chronic pancreatitis detection. It's a definite clear signal that you can get for the nitric oxide and hydrogen sulfide. They also looked at how humidity plays a role in the background noise. So if you have to, they've calibrated the nickel and the palladium sensor against different levels of humidity. And they have the current response, and they measured the current response, compare that to the actual sensor response at each of these conditions. And they show that the sensor can be interfered or be cross-sensitive to humidity in some cases. So from a device standpoint, usability standpoint, the humidity correction has to be happening as well. But in a positive note, you can sense humidity in a gas stream. So there are devices today that need gas or humidity sensing. So this could be a possible way to get humidity at least to 70%. There's a chance of detecting humidity in gas streams. So try to summarize it. Rapid response, every one of these signatures showed rapid response, all moly sulfide to all of the functionalized materials. The moly sulfide with palladium at a high selectivity to nitric oxide. The nickel functionalized material showed H2S. With the zinc oxide, they showed some other behaviors with ammonia as well and nitric oxide. Moly sulfide had multi-component capability, but once you start getting into multi-component capability, there is cross-sensitivity. So you have to be careful about needing multi-component capability. In automotive devices where they look at average exhaust, multi-component capability is good enough. But for a biomarker application, you need high selectivity without any cross-sensitivity. So the palladium and the nickel were chosen as the best material for limiting the cross-sensitivity. And drift-wise, there was not much study, primarily because they tested in seconds. Typically, sensors take longer time to drift. But over the time of the test, I would say that the nickel moly sulfide did show more repeatability. And the palladium-based with the nitric oxide selectivity did not show as much drift response. So I think that was the end of the presentation. Stop sharing. Any questions?
Great. Thank you, Mani. That was very nice summary. Excellent.
Thank you.
I took the time and really walked us through. So it was very nice. Let's open it up for Q&A, discussions, thoughts.
I really thought the principle of operation slide was really helpful because you took an extra effort to kind of explain and just split it up rather than just what I thought. When I read the paper, I was like, this looked different in the paper and you presented it in different ways. I was able to understand it probably in a better way, I think. So yeah, that helped a lot.
Yeah, the paper, they actually crammed up the information because they knew the principle better than most of the readers.
Yeah, yeah.
So I had to kind of go online, look it up a little bit, and I understood. Obviously, it's based on semiconductor principles. And yeah, if you understand the principles, it's easier to apply it. What I thought was interesting is the charge transfer piece associated with how you can impact the conduction band and change. I thought that was a very interesting approach.
Yeah, also, it was very interesting to see how the palladium, when it even though it has a higher work potential than MOS2, it kinds of reacts with nitrous oxide and forms a lower work potential. So that's why there's an increase in the response. So that was something new to learn. So
yes, yeah, and they talk about both of those in a sense where they actually talk about two mechanisms right there. Which one they decided to pick themselves. Yeah. You're right. The work function is an important parameter because it depends on which material donates that electrons. The functionalized materials, if it is a functionalized material, then the limit or the detection limit or the resolution gets impacted because you cannot transfer that much electrons because your surface area is limited to your functionalized material, not moly sulfide now. So you've lost the ability to access the high surface area from the moly sulfide. So it does impact it that way as well.
Yeah, one thing when I was first reading this paper and like looking through it, surprised me, like the biosensor part. I never thought that would be applicable to like a toxic gas sensor. I mean, when I first like saw the heading, like I think in last week's science review, it seems like, oh yeah, it'll have applications for like carbon monoxide, NO, all that, but I never thought like it could help detect those diseases. So that was interesting.
Yeah, absolutely. And I think Chalk knows this. For example, if you buy sensors to detect, for example, there's an interference with CO, or if you're looking for CO, there's an interference with the hydrogen. So you null the response of one gas to be accurate to say that it's a response from the other gas. So they used nulling effects. So they use 3 electrode configurations to null one gas and say that specifically the relative response comes from the other gas. We didn't talk about much here, but I know, for example, the CO hydrogen, they use a 3 electrode system to study that.
Yeah, that's one of the thoughts I was thinking about how this could have been, more value could have been added here is
Yep.
through mechanisms like that, designs and engineering designs like that to address the cross sensitivity issues.
Yes.
Right. So you can come up with a combination of materials design and the electrode and the cell design
True.
to take care of the mixture of gases. The other thing that occurred to me was related to the partial pressure of oxygen. So if that could have been an indirect way that they understand the sensitivity issues,
True.
right? So, for example, you cannot predict whether it's going to be oxidizing or reducing gas that's going to be interfering with your sensing gas. An indirect way of getting at that would be impacting the oxidation or reduction capability by changing the oxygen partial pressure.
Right. True.
Yeah, so that's.
Yeah. And I think that would have been a good idea, because if your partial pressure is different, then the number of electrons you grab from the conduction band would have been different.
Correct.
You plotted it as a function of oxygen concentration.
Exactly.
Which would have been interesting if there is good resolution.
Yeah.
You could be an oxygen sensor in the car.
Yep.
What they use in the car. I don't know if that's what you were thinking.
Yeah. Similar, yeah. Along the, so what I was thinking is a sort of a differential one.
Yeah.
Where a combination of the electrode design and the partial pressure, try to see if we could detect that.
Yeah.
And one more, I think I just wanted to ask this. So when palladium reacts with NO, right? So it forms this palladium NOx complex. So why doesn't the why does the response would not increase when it is NO2, right? So that question I had, I thought maybe when we discuss this, it's probably better that maybe we all can discuss, so we know, I would know that, because I was thinking if it forms the NOx complex with palladium, why not NO2? Why just NO? There's an like a increase in the response, right?
The lone pair of electrons, I don't know if that plays a role, Chuck, but
Yeah.
there are for sure better absorption with NO than NO2. But I don't know if that alone is the reason, but it forms a complex. I don't know.
Yeah, I believe it's related to the stoichiometry was my first thought, even when you brought up NO versus NO2, the number of electrons available to really create that bond.
Okay.
Between palladium and NO, right?
Yeah.
NO, when it's NO, you're able to form that, but if it's NO2, there's already a compound that it's stable,
Already
much more stable than NO, I guess.
Yeah.
That
makes sense.
Better absorption, your binding energy is probably favorable.
Correct. With NO. Yeah.
Yeah, which is actually kind of interesting. If you think about it, catalysis, you want it to bind.
Correct.
And then you want it to bind so that there can be charge transfer, but you don't want the product to bind. So you want the product to leave the surface.
Yep.
But you don't want, so you want the just the amount of right binding energy for the gas molecule. Once the charge transfer happens, you don't want any more binding. You just want to leave the surface, right?
And they didn't look at CO on this, right?
No, they didn't. They say CO on the slide, and then really don't look at it. And I thought there's a lot of work with CO, but I think molysulfide with CO, I think there's probably other work people have done with platinum and platinum especially.
Okay.
But I don't know if there's what else. I don't know if there's a gas sensor today which is not platinum based for CO. I don't know if there is one.
I don't know. I'm not sure. So that's why that will be good. But I mean, they do bring up the humidity impact and other things. So
yeah.
There's
a cross sensitivity there, but then they also talk about how humidity can be in one line. They talk about how humidity you can also use that positively. So the background noise you have to separate, and you have to know that, obviously the temperature at which you're operating. So you have to keep the background the same as that's the bigger message there. If you change your background, that's going to change your, the calibration curve.
Great. Okay, if there are no further questions or comments for discussion? Mani, you want to share next week's paper?
I'm so sorry. Yeah, that's right. Give me 1 second again. I'll stop.
I can share if you want.
Yeah,
Yeah.
Got it. You got it? I got it.
Okay.
Yeah.
Yep. Ayyappan, you'll be leading next week's discussion, right?
Yes, yes.
Yeah, go ahead. And
Yeah. So, yeah, hello everyone. So next week we'll be going over the electrochemical detection of serotonin using zirconia oxide nanoparticles on a modified carbon-based electrode. Also open access journal from Journal of the Electrochemical Society.
great. Thanks, Ayyappan. Thank you all for joining. If you would like to lead a paper discussion, please send us an email at info@vetrilabs.com. That email again, info@vetrilabs.com. Thank you.